same. We derive this one till this much. So we can write for the B component also mobility. What is mobility? Velocity of an atom per unit chemical potential gradient. Yes or no? So we took the PA equal to mobility multiplied by driving force, which is minus del mu del x. Then we put mu equal to mu naught plus kt ln AA. A is gamma A Na. We took that derivative with respect to x to get to this equation. And so similarly for component B, we can write mobility of B this should be all subscript should be of that of the component B. Both this mobility, the thermodynamic factor and the intrinsic diffusion coefficient of any component should correspond to a particular composition. Okay. Interdiffusion coefficient or chemical diffusion coefficient also corresponds to particular composition. We can measure at a particular composition. At C only we measure, so if at different C the value will be different. See, here also your mobility, your thermodynamic factor, which is given by this, and also this one, intrinsic diffusion coefficient, corresponds to a particular composition. So we can, from that, and from Gibbs-Freer equation, from thermodynamics, we get that for different components, this del ln gamma over del ln x are equal. So for A should be equal to del ln gamma B del ln x b. So that comes directly from thermodynamics. So if that is the case, so the inside the thermodynamic factor for different components are same at a particular composition. At a particular composition, thermodynamic factor which is within the bracket is same. So we can say that dAc over dBc is the ratio of the mobilities and in an ideal solution this becomes 0. Del ln gamma over del ln x, for ideal solution it is 0. Activity coefficient is 1. For ideal solution, this within bracket term becomes 1. So for ideal solution, dBc equal to mbkt or dAc equal to makt. So the intrinsic diffusion coefficient is multiplication of two factors, one coming from the ideal solution in which random jump happens, random jump of atoms happens, multiplied by the non-ideality given by this thermodynamic factor, which the value of which actually comes into picture. It acts as a weight, W-E-I-G-H-T, weight in the diffusion of atom over and above the random jump. If there were random jump only, which happens only in ideal solution, the intrinsic diffusion coefficient will be given by mkt, multiplied by the thermodynamic factor if to take care of the non-ideality. For phase separation type of cases, this thermodynamic factor even become negative. Then your diffusion coefficient will be negative. What does it mean? Uphill diffusion.
And when will be it will be negative?
Thermodynamics will tell you that this is related to the curvature of the Gibbs free energy with composition. If your Gibbs free energy versus composition at a certain composition is negative curvature, then it will be negative.
Can I repeat this for
With them. What I am saying that for ideal solution, this becomes
zero?
zero. So 1 plus 0 is 1. So for ideal solution, dBc equal to mbkt or dc, intrinsic diffusion coefficient of any component, is mobility multiplied by kt. For non-ideal solution, it is that. In ideal case, it is just the random jump through which the diffusion happens through thermal agitation. And in non-ideal case, so this is the added factor that is acting as a weight over and above the random jump. And in tracer diffusion coefficient, for a homogeneous alloy, if you put a very thin layer of isotopes of the component A, say you have an homogeneous alloy of a particular composition on a plane surface. If you put few numbers of isotopes of A and anneal it for a specific time and measure the profile, and from that equation the solution to Gibbs free, the fixed second law, we had that minus x squared over 4 dt. So if you use that equation, there also this becomes zero, because the homogeneous alloy, there is no composition change, the xb is not changing, so this is not coming into picture at all. This becomes zero. For the tracer diffusion coefficient measurement using small number of radioactive isotopes in an homogeneous alloy of a particular composition, because it is an homogeneous alloy, composition variation is not coming into picture, so this becomes zero, this factor becomes 1. Your actually for tracer diffusion coefficient dA should be MAKT and dB equal to MBKT. So for ideal solution, dBc equal to MBKT, dAc equal to MAKT. For tracer diffusion coefficient, because there is no composition coming to picture, there also tracer diffusion coefficient will be MAKT, MKT for each component. Okay, but mobility depends on the alloy composition. In the homogeneous alloy, what is the composition of that alloy? Mobility. So if you change the composition of the alloy, and you will find different mobility. So mobility values are function of composition. Thermodynamic factor values are function of composition. So as a result, the dBc, dAc are also function of composition. So did we talk about, we had this equation, hold on. Can you remind me till what equation we discussed in the last class? We had this equation, del CA. Okay, we discussed till that part.
Yes.
Till intrinsic diffusion coefficient. Now intrinsic diffusion coefficient you can conceptualize it as it's a diffusion coefficient which characterizes diffusion of an atom that feels a thermodynamic force. So it's moving. So it is with respect to the lattice. If you are sitting on the lattice, then you are seeing that atom is moving or it is feeling some force. It is minus del mu del x. So it is moving. So minus del mu del x, that is the driving force, multiplied by the mobility will give its velocity. So velocity multiplied by the concentration of that atom will give you the flux, and that flux corresponding diffusion coefficient is your d superscript c, intrinsic diffusion coefficient. Now the total flux from outside, now if your marker, the lattice plane itself is moving. If you are sitting on the lattice plane and you are seeing that flux of A, that is the actual diffusive flux under certain driving force, but your lattice is also moving. Say that, and due to that movement, see, the lattice plane, say if it is moves at a velocity v, say the marker is moving at a velocity v. Marker movement is nothing but the lattice plane movement. That v multiplied by the concentration of A atom will give you a flux. That is the flux of the lattice. Due to lattice plane movement from outside, I am seeing the A atoms are moving. Even though, for example, if you consider there was no driving force for A to move, still you will see A is moving because the marker plane is moving from outside. So flux of A due to that lattice plane movement plus intrinsic flux of A should give you total flux from outside of the crystal, or from one end of the crystal. That is the total flux of A. What is this? This is nothing but this one.
V is the velocity of this marker plane.
V is the velocity of the marker plane. So one is this is purely the diffusion thing, which is the velocity under driving force. The diffusive flux of A under a driving force of chemical potential gradient. This is just because of lattice plane movement. So summation of those will give you the total flux of A when you are outside of the crystal, with respect to outside of the crystal, or with respect to one end of the crystal. That is the total flux of A. And when we wrote that del C del T equal to del CA del T equal to minus del X of d tilde del C del X. When we defined our interdiffusion coefficient, interdiffusion coefficient is a measure of how quickly the homogenization happening, how quickly the intermixing of the atoms are happening, sitting from outside of the crystal. Okay. So see this minus d dc dx.
What is JAD?
You tell me what it is. I told many times. Now you tell. If you are wrong, then I will tell you.
Intrinsic flux.
What, Swan?
Intrinsic flux.
Intrinsic flux. Under the potential gradient, chemical potential gradient. Intrinsic flux. That is diffusive flux. Intrinsic flux. And this is because of the lattice plane movement from outside. So it is sitting on the lattice, whatever intrinsic flux you are getting. And from outside, if you have to see the total flux. Now this minus d dc dx, minus d dc dx, if I take this minus inside, minus d dc dx is the flux. So that flux is the actually total flux. When you, the d tilde is actually characteristic of the total flux. You are looking from outside, d tilde is a measure of how intermixing, how quickly the intermixing happens. So it is from outside, the total flux of any component A. Sorry, I did something else.
No minus one.
It should be, okay, yes. So it was d tilde del c del x, and there was no minus, there should not have been minus. So it is the minus j. It is a minus j. Right? That was the mistake. So, and